So good afternoon. Now we have this as second video for your flexural member. Already we have seen when my load is along the longitudinal axis, member will act as axial, and when it is perpendicular, then it will act as mm, beam or flexural member. In last video, we are generally questions which are related with laterally supported beams. Now we are with laterally unsupported beams. Some questions we have that is at the end which are related with your laterally supported and unsupported when we will talk about the checks. Now, what is formula for moment of resistance for laterally unsupported beams? So, if we will go to this MD, we have that is beta B ZP into FBD. So now beta B already we know we have for compact and plastic value is 1 and for semi-compact value is Z E upon ZP. And then FBD we have design bending compressive stress. So main we are with again design how to calculate this FBD. What is formula for design bending compressive stress? Now we have XLT upon gamma MO. Now try to understand this. If we will go to FCD, then you have that is reduction factor into Fy upon gamma MO. So in this flexural member, this LT comes over here. And that is the change actually. Otherwise, if we will compare the formula, then you will see the terms we are being near about same, or the formula we have more or same, that is in FCD and FBD. Then XLT, bending stress reduction factor, there we have X as reduction factor. Then what is formula for this? Then you can see this, there we have formula phi plus phi square minus lambda square to the power 0.5, and lambda value we have to take in single angle, that is from that 7.5. Now here you can see XLT phi LT plus phi square LT minus lambda square LT to the power 0.5 means root of, and this value should be always less than or equal to 1. So this value should not be greater than 1. Then what is formula for phi LT? Then we have phi LT 0.5 1 plus alpha LT lambda LT minus zero point 0.2 plus lambda LT square, and then alpha LT is the imperfection factor. We have there alpha as imperfection factor, and there we have in compressive stress four classes A, B, C, D. But here we have only two values of alpha LT, which depends upon your section. So for rolled section value is 0.21, and for welded section 0.049. So for which value we are going to get this value of phi LT larger one. So you can see alpha LT we have for 0.21 for rolled section, and value we have that is 0.49 for welded section. Now you can see, so phi LT for rolled section is less than phi LT for welded section. So this you should be in position to explain which will increase value, which will decrease value. So phi LT for rolled we have less. And if we will put over here, so my value of XLT, this is for rolled greater than XLT for welded. So now try to understand, phi LT is greater for welded, but as it is in denominator, so when we will calculate XLT, so denominator is more. So we can say denominator for rolled is less than denominator for welded, and as we have denominator for welded is greater, so automatically my XLT for rolled is greater than XLT for welded, and therefore my value for rolled section is always value of FBD is always greater for rolled section than that of welded section. So this you can be in position to explain the values. Then which table is required for FCRB? So table 14 you can see, and in table 14, so this is actually HF upon TF, and HF we have center to center distance between flanges. center to center distance between flanges. And then as your value, this depends upon KL upon R. As your KL upon R that is increasing, your value of FCRB that is decreasing. And then again you can see if your HF upon TF is increasing, then your value of again FCRB that is decreasing. So anyway, if you increase the value, that may be of lambda or that may be of HF upon TF, your value of FCRB decreases. For which decreases? If this increases, then FCRB will be decreased. And FCRB and FBD, what is the relation? If your FCRB decreases, your value of FCD, that value of FCD also decreases. But for FY increases, my value of FBD also increases. So for alpha LT 0.21, your FBD values are greater than alpha LT for 0.49. Now, if you will see here, there is very small reduction for this FCRB. As you go below, again you will get very small decrease in the FBD value, that is hardly 1 to 5%. So that is not much decrease in the value. So, but you can keep in mind, if your value of FCRB increases, your FBD decreases. So we so for lambda increase, FCRB decrease, and if FCRB decrease, FBD decrease. So for less value of lambda and HFTF, your FCRB increases, which increase your FBD. So you can see these are inversely proportional. Lambda and HTF are inversely proportional to FCRB, and same for FBD. Then for we have values in table, that is for FCRB 10 to 10,000. If my for FBD, if my value of FCRB less than 10 and greater than 10,000, then we cannot find value from FBD, and we have to go for basic formula. We have to find lambda LP by using FCRB. Knowing lambda LP and alpha LT, we can find phi LT. Knowing phi LT, we will find XLT. And by XLT, we will get value of FBD. So we have to use this formula when my FCRB value is less than 10 and greater than 10,000. Because below 10 and above 10,000, values are not available in table number 13A and 13B, which are the locations for web buckling and crippling. So we know web buckling, that is at neutral axis. So we can have, if we will draw this diagram that is of beam, then we can have this beam in this fashion. And this beam will buckle, that is at neutral axis only. So buckling you will see. So we have this buckling that is at neutral axis. So we have here. And where we have crippling, so crippling we have that is at the junction, that is junction of web and flange. Your web will crush. So here your web will crush. Why web will crush? Because we have area of flange is much more, and suddenly abruptly we are going to transfer load from larger area to load on smaller area. So this will be width perpendicular to this, we have thickness, that will be now web area, and here we have this will be width and perpendicular we have thickness. So at web, this is suddenly decrease in the resistance area for shear, and therefore it may crush your web, that is junction at web and flange. So we have that is at the junction of flange and web. Now what is the angle of dispersion? So if you remember, we have already seen and we have plotted in sheet also. In case of your this is bearing length. So whenever you will plot it, you have to plot bearing length, and then you are going to be like this, and you have that is at neutral axis, and we have this value B, and this angle of dispersion is 45 degrees. So this will be B1 we can say, and then we have this will be B bearing length, and then we have these values actually. If we have H be the depth of the section, then we have these values as h by 2 and h by 2. So total we have h. Then b1 is b plus h, where b is bearing length and h is depth of the section, because this becomes angle 45 degrees, so isosceles triangle. And then h by 2, h by 2, we have the we have the sides. Then in case of web crippling, we have already seen that we have this crushing is at the junction of this, and then we have to draw this, and then this angle we have to plot. Again we have this will be bearing length, and from this we have to plot this. So we have this total thickness or depth, we can say, and this slope we are going to be 1 vertical to 2.5 horizontal. And we have this is our thickness of flange, and this will be considered as root of radius. That is for flange and web. So we have two root of radius, one that is at flange, this root of radius, we can say this root of radius, and second we have this one. So we have to take this root of radius, and therefore if we will see this, then you have this will be b value, and this value 2.5 in bracket t plus r, and therefore you will get this b1 or b2, you can say, which will be b plus 2.5 in bracket t plus r, and we can find likewise this, and then we can find values of strength over there, and that will be greater than your shear forces. So these are the some question. Again we are from flexural member, so in next video we will go with other units. Thank you.